Today I'd like to talk about traveling salesperson art. And this is a really neat Da Vinci-esque concept that marries art with a lot of really cool math and algorithm ideas. So it's actually based off of an early 2000s paper by Craig Kaplan and Robert Bosch. You can see right here. And to illustrate what it does, let me first show you. I got this picture from Christopher Michel on Flickr, which is Creative Commons, of these emperor penguins, this emperor penguin family here. First, what I can do is create something called a stipple pattern, which is just a bunch of dots that I'll put down, and the density of the dots is proportional to, usually to the darkness that you want to portray, although there's certainly flexibility with the dots that you put down, somehow you want them to represent the image. And this is already a pretty cool idea, but we can take it one step further and actually notice that if I color this a certain way, these colors are going to give me an order in which I can connect the dots without picking up my pencil and without crossing over something I've already drawn. I can actually connect all the dots in a big loop. And that's traveling salesperson art. So let me show you a little video I made depicting this. So here's our emperor penguin friends, and you can see I'm connecting the dots and I'm going around and around and around. Notice that it never crosses itself, this path that I'm drawing. And eventually it wraps back around exactly to where it started. So that's what we're going to do. And you know, why would we do this? I don't know. It's art. It's a cool idea. I mean, you know, and it's also going to give me a chance to show a bunch of very fundamental algorithms. And so I thought, why not? In fact, I actually made an assignment on this when I used to teach data structures. I'll link to it. It's kind of a capstone assignment in data structures. So you can try it yourself if you'd like to at the end. But I'm going to keep this pretty self-contained. So let's start at the beginning, and we'll try to do this. All right, so let's get started. The first thing we have to do is create a stipple image. So I'm going to go ahead and load in this penguin image. So I'll use a scikit-image library, pretty standard library here. Try not to take too much for granted, so I'm not going to use any fancy libraries, just kind of basic things. So this is, for me, is in this directory, penguins.png. And if I print out the image, I can see, in fact, it's actually, if I look at the shape, it's a three-dimensional array. This is the row, so this is a height of 765 pixels. This is the column, so width of 978. And then there's an additional three wide dimension, which is the color channel, red, green, and blue. So it's really a stack of three images, one for each color channel. And the other thing you notice, if you look at the type of it, it is all numbers between 0 to 5. And if I were to look at, say, D-type here, it tells me this is uint8, so unsigned int 8 bits. So this is integer values between 0 and 255 for the red, green, and blue channel. Oftentimes, though, when you do image processing, you want to convert this into a floating point representation, because sometimes you're going to combine pixels, average them, filter them, do weird things with them. That will take them away from those 256 possible values for 0 to 255. So it's a little better to work with floating type. Maybe I want a pixel that's 254.2 or something, right? And so actually the convention is, if you're going to do that and have a floating point representation, you remap the image to the range 0 to 1. So I'll say image.asType float, and then I'll divide by 255. So we're going to remap to the range 0, 1. All right, and in fact, if I go and look at this, matplotlib still knows how to deal with this. Even though it sees things in the range from 0 to 1 now, it still knows how to plot them with the proper colors. Okay, so we're going to take it step by step, just getting started here. But the next thing I want to do is, I'm trying to create this stipple pattern where I put down more dots in regions that are darker. So I want a representation that tells me how dark things are. I don't necessarily care about the color, but I want to know if there is dark or light. So I want something for the brightness. And so what we'll do is convert this to grayscale. And I actually wrote this part down ahead of time because I can never quite remember. So I'm just going to look at my notes over here real quick. I usually don't cheat like that, but here we go. So I'll say here image is equal to, okay, so what we have here is we're going to take the first channel, the red channel. That has the weight 2125. Okay. So we're going to take this weighted average of red, green, and blue. The next one is the green channel. That actually has the biggest weight. So that is going to be times 0.7154. So interesting, we actually perceive brightness a lot more in the green channel than the red channel. And actually the last one, the blue channel, has the least of them all. So that's going to be 0.0721. Okay. Okay, so what I've done here, if I print out the shape of this, is I've actually reduced this three-dimensional array to a two-dimensional array. So this here was saying take all the dimensions and then the zero index in the last dimension. So take the rows and the columns and just a zero index. That is the red channel. It's a two-dimensional array. And take the green channel. That's another two-dimensional array. And then take the blue channel. Scale each of them by a certain amount and add them together. So what we get is a two-dimensional array. If I look at this two-dimensional array in matplotlib, it's actually going to put on its own color map. So here's the default color map. If I switch that color map to gray, then I get the right answer here. So this is what I'm looking for. I want, in fact, if I throw in a color bar here, I see a low number for the darker regions and a large number for the lighter regions. And that's exactly what I want. And I would like to sample points more in the darker regions than the lighter regions. So let's try to do that now. So let's try to create a stipple pattern and sample points proportionally to how dark things are. So what I'll do here is I have to think of this image a little bit more like a probability density function. And somehow what I want is the darker regions to have a higher probability than the lower region, than the lighter regions. So what I'll do here is I'll make an array called probability. And I'm going to make that to be 1 minus the grayscale image. And actually, just to make this a little bit clearer, let me call this image grayscale. And so probability is going to be 1 minus image grayscale. So what that'll do is I'll make it actually so that it's going to look a little weird when I show it. Actually, let me use a different color map. I'll use a color map called magma, which is very good. It's a perceptually uniform color map. We can take a look here. So what I'm seeing here is the numbers that are close to 1 are higher. That's where I'm more likely to throw dots. And the numbers close to 0, I'm less likely to throw dots. So I'm going to end up with more dots on the head and the feather here, and maybe on the little guy here, or gal, and more dots over there. So how do we make that happen? How do we actually throw down the dots now, like throwing darts at this, where I'm more likely to throw darts here? So how do I do that? Well, first, let me make sure that all these numbers sum to 1. So what I'll do is okay, so the numbers are between 0 and 1, so let me divide them all by the sum of them. And so now, they're in a very different range. Notice they're actually pretty tiny numbers because there's a lot of pixels. So when I sum up all these weights and divide them by the sum, I get very small numbers for each individual pixel, but now the good thing is they all sum to 1. So if I were going to sum these probabilities, I would get 1. Oh, I should say probability. And that's good because now it's a true probability mass function. And so what I can do is sample from this. And to explain how the sampling works, it's actually a little bit easier for me to draw a picture first to depict the algorithm. So here, let's imagine that we had these 4 pixels, and the brightness here is proportional to the probability that I'm going to choose that pixel. So it's more likely that I'm going to choose A than I'm going to choose any other pixel. And it's actually the least likely that I'm going to choose C here. And notice that these numbers sum to 1 because they're probabilities. And so what I can do is lay these different pixels out along the number line from 0 to 1. And I'll partition that number line in a way that the lengths that each of these take up are proportional to the probabilities. So A, let's make that take up from 0 to 0.4. And then B, what I'll do is B is 0.2 probability, so I'll make that length be only half as long. So this here, let's say this is from 0.4 to 0.6. So the length of the interval that B takes up is only 0.2 long. C is going to be even shorter. C is only going to be half of that, actually. And so in order to do that, I'll have to go from 0.6 to 0.7. And so what I'm doing here is something called a cumulative sum. So I'm going to accumulate all these numbers that I've added up so far. And then the interval of the next one is going to be the accumulation plus the probability of the pixel that I'm trying to throw down there. So here's what we find. A takes up from 0 to 0.4, B is from 0.4 to 0.6, C is 0.6 to 0.7, and D is 0.7 to 1. And so now what I can do is think of this as a one-dimensional problem where I'm just throwing darts at this line with uniform probability. And I will assign, I'll say, okay, you drew pixel A if I land in this interval. You drew pixel B if I land in this interval. So for example, let's say that shows 0.5, right? Well, that's going to go to pixel B. Let's say that shows 0.8. Okay, that's going to go to pixel D. Let's say it shows 0.2. Okay, that's going to go to pixel A. So all of these have a non-zero probability. If I run this experiment many, many times, and I look at the proportions of the times that I've chosen each of these, they will approach these numbers as I draw more and more samples. So actually, this is not too difficult to simulate in NumPy. What I have to do is accumulate these numbers, so start, add up these probabilities in a running sum. And NumPy has a method called cumulative sum, CubeSum, that does this. So I'm starting with this two-dimensional array called probability. So just to remind you, it's a two-dimensional array. Let me first flatten this. So I'll make an array called C probability. So it's going to be probability.flatten. And actually, maybe before I do the whole thing out here, let me actually run through this example. So I had the probabilities before. It was 0.4, 0.2, 0.1, 0.3. Yeah, let's just look at the cumulative sum on those. So if I were to say cumulative sum of 0.4, 0.2, 0.1, 0.3, I get these 0.4, 0.6, 0.7, 0.1. So that's great. Actually, though, I should put in a 0 at the beginning because I want to make sure I have all the endpoints here. I was missing the endpoint 0 there, right? That's important. So I have 5 endpoints and 4 intervals between them in this example. So I always want to have that 0 at the beginning. So anyway, now I've got that. So let's do a similar thing with this C probability. So actually, if I look at this, there's quite a lot of numbers here because I've flattened this entire two-dimensional array into a single one-dimensional array. And actually, I really want this to, let me make this have a 0 at the beginning. So I'll say C probability equals empty.0 1 plus probability.size. So I want to have that extra 0 here. And then I'll say C probability 1 to the end is equal to probability of flatten. So now I have one extra element. Okay, so now I need to write the code to actually throw down a bunch of random samples in the interval between 0 and 1. And so let me first define a variable called number of samples, or n samples. I want to make that 2000 because that's what I used in the example before. Okay, so what we got to do is throw down n samples numbers between 0 and 1 and determine the interval for each one, which will help me to decide what pixel it goes to. And so actually what we're going to do is just do a binary search. So for each, so to find the interval, do a binary search on C probability. And so then the overall time complexity is big O of the number of samples times the log of the number of pixels, right? Because for each sample, I do a binary search, which takes logarithm of time to find the interval, and then I take the pixel corresponding to that interval. Now, normally I would make my students code up binary search, if this were a data structures class, but NumPy already has a method that's going to help us a lot here. So I can use this method called search sorted, which does binary search. Because this is an array that goes in ascending order, I can use binary search. And so we could, therefore can use this method called search sorted. So here I'll say indices equals np.searchSorted. I'll give that C probability array. And then I'll say, okay, I'm just going to choose, so the np.rand method. And let me actually seed this real quick. I found out recently this is a legacy method, but this is the only one I can remember off the top of my head. Usually you're supposed to make actually a random number generator. I forgot how to do that. You make it its own object, so it's a little bit more contained. But anyway, for now, I'll just do a global random seed. Please forgive me. Anyway, so I'm going to choose as many random numbers between 0 and 1 as there are samples. Oops, Chris, I meant to say np.random.rand. There we go. Okay, good. So now I have a bunch of indices, and each one of these indices tells me which pixel it is that I want to take. They're going to be all over the place, but they should be proportional. This is a little odd, though. I shouldn't be getting all the same number. So let's see what I did wrong here. So let's look at the documentation real quick. np.searchSorted. Okay, so the first argument should be the array that I'm searching in. And the second argument should be, so let's just check. So C probability, the first element should be 0. The last element should be, I forgot to do the cumulative sum. I made a big deal about the cumulative sum. I totally forgot to do the cumulative sum. I just saw it there. Okay, but let me finish that debugging there, because what I should see is that C probability 0 should be 0, and then the last element should be 1. That was not the case when I forgot to do the cumulative sum. They were just the probabilities. I need to accumulate these numbers along the interval, like I was showing before. Okay, good. So I fixed that. Great. So now let me do this again, and if I look at the indices, okay, now there are a bunch of different numbers. So let's see, what are they? What I have to do is actually put them back. So this is in a one-dimensional array. I took each row of this matrix and lined them all up so they made one big one-dimensional array. That's what the flattened method does. What I need to do is go backwards. So what I'll say is indices equals np.unravel index. So I'll take each one of these and say, hey, you know what? These were actually from a flattened array, which was originally a different shape. The shape of that is probability.shape. So I'm going to undo the flattened thing and put these indices back into 2 dimensions. So before, when I print them, it's giving me the one-dimensional index. Now when I print them, it's giving me actually, it's giving me 2 arrays that are parallel to each other. The first one tells me the row that it goes in. The second one tells me the column that it goes in. So here, let me say, I'll just say rows, columns equals that. Okay, so now what I can do, let me actually plot these on top of these probabilities and see where the dots end up. And we'll see if we're getting anything that looks like it's sampling proportionally to the darkness there. Or actually to the lightness, rather. So yeah, let's draw this, and I'll scatter on top of it. And actually, this is always a little bit confusing. The rows are the y coordinates, and the columns are the x coordinates, right? Rows goes down, that's y. Column goes to the right, that's x. So I have to give the x coordinate first when I scatter, and then I give the y coordinate. I'll make these kind of small dots. Put the color bar before the scatter. Okay, so it's a little bit hard to tell, but I do think I see more dots on the interior of this little guy, and certainly around his head where there's brighter stuff. I see more. Yeah, I think that's basically working. Let me just, for the sake of illustration here, let me draw 10,000 dots. And I think you can see a little more here. See, there are not as many down there. But this isn't quite as clean as the distribution that I showed in the beginning. So let me do some stuff to this probability to make it a little bit better for sampling these points. Okay, so if you go back to this result that I had from before, you'll notice that in the light regions, we don't have any dots at all. So if we put dots there, it might get a little messy. I mean, it's up to you, but I think it would be harder to discern that these are penguins if it was like zigzagging all through the center of them. So that's one thing I might do. So what I'll do is if the pixel has a low enough probability, I'll just round it down to 0. So it's a little bit easier to see before I do the normalization here. So let me define some thresholds here. I'll say low threshold. Let's say if the probability is less than, maybe I'll start with 0.4. So here I'll say, okay, if the probability is less than 0.4, then I'll just round to 0. And then I'll do the normalization. Okay, so now you see it's just not going to choose any dots there. So if I run this again, now we'll really see if this is working. Yeah, okay, good. So that seems like a little bit closer to what I want. Another thing I can do is I can actually increase the contrast a little bit, so I can put these on a square root curve. So if I were to say, before I normalize, if I were to say probability equals probability, actually there's a couple choices I have here. Okay, that actually decreased the contrast. That's not what I want to do. Compress the contrast. I want to expand the contrast. So let me square it instead. So you notice there that everything became a little bit closer together. I actually want to stratify the probabilities a little more. So now I'm making the head stand out. So actually, it'd be helpful if I save these images side by side. So let me just take a screenshot of this real quick. And yeah, so yeah, let's say that I increase the contrast. Maybe I'll cube it actually. And really this should be a parameter. So I'll call this contrast equals 3. So the bigger I make this number, the more things are going to stand out that are a little bit brighter relative to everything else. So you see if I make it 10, I'm really only getting that stuff. I think 3 is probably a good number. So let's try that. So, you know, this is something you play around with. I think this is probably fine. Actually, I've taken too many samples. Let me get back to 2000 and see if I'm happy with that. Okay. So yeah, anyway, I'll keep moving now. But you can see these are some of the things that you can play with. Actually, I think I'm pretty happy with this though. This seems to be working how I wanted it to work. So give me a second and I'm going to put this in a method and clean it up. Okay, so you can see here's a little method I made. And all the code we did is really not that much. We just had to think very carefully about it. And so here it is all together. So I'm returning a whole bunch of stuff that's going to help us with subsequent steps. So both the rows and the columns of the stipple points that were chosen in the image. And then the image itself that was loaded, which I'm showing here, and then the probability image, which we're going to return to. Okay, but looking at this stipple pattern, it's a little bit messy. Compared to the original example that I showed with the penguins, here I'll bring it up again. These points are kind of noisy. So you look at the original video, you can see they're distributed a lot more evenly. And in fact, if you look at the Traveling Salesperson Art paper, you see they're using a technique called weighted Voronoi stippling by Adrian Secord. And you can see the little teaser image here. These stipples are much cleaner. I mean, it looks like the points are more evenly distributed, spaced out, and it just looks more aesthetically pleasing. So the way they do this is by constructing something called a weighted Voronoi diagram. And what this is, I'm going to show a little interactive thing here on this website by Alex Baytel. Let's pretend I placed a few stipple points down, like this. What I can do is partition the plane into regions which are closer to a particular stipple point than they are to any other point. So this red polygon here contains all the pixels that would be closer to this stipple point than any other stipple point. And what you could do is say, okay, for each of these regions, I'm going to move that stipple point to be towards some center of mass of some sort of these polygons. Because notice here, this one in particular, it's kind of close to the edge here, right? You see it's really not towards the center of this polygon. And so what they do in the still paper is exactly this. They compute this Voronoi diagram, this partition of the plane, and for each region associated to each stipple point, they then move the original stipple location, which is shown in the big dot here, to a smaller dot, which is some center of mass. And the center of mass is actually just going to be weighted by the probability. So the probability is going to be the mass here. If you had uniform probability, it would just be the centroid of these polygons. But we're going to change it to be weighted by the probability. And so they're showing here, yeah, if you do this, you're going to get, I think in this example, they probably have all the weights the same, so they get a pretty evenly distributed thing here. But, yeah, so that's what we're going to do. Now, I wish I had time to talk about Voronoi diagrams. I'll do it in a future video, because it's a really cool topic. And I'll explain the math and the code to compute it. But for now, I'm just going to black box that a little bit, and I'm going to use a method which is in scipy. So I'll say from scipy.ndImage import, let's see, it's called Euclidean distance transform. So the EDT, or Euclidean distance transform, is a discretized version of the Voronoi partition that I was showing here. And it's perfect for what we need to do. So let me show you how to use this. What I need to do is set up this mask image. So I'll say mask equals .zeros image.shape 0, image.shape 1. So I'm going to make, actually let me make this all ones to begin with. I'm going to make an image that has as many rows and columns as there are in the image. And then what I'll do is I'll say, okay, anywhere where there happen to be a stipple point, because these are chosen at pixel locations, anywhere that there happen to be a stipple point, I'm going to set the mask to be 0. So I'll say mask rows columns equals 0. So that's what I returned from this method here. And so really, I'm encoding the stipple information in a different way, but it's the same information. So if I were to look at this image, it looks like this. Okay, so it's mostly 1, but it's 0. It's a little bit hard to see, but there's zeros any place that at a pixel where we happen to choose a stipple point. So this is the format that this particular library for computing Voronoi diagrams needs. So now what I'm going to say here is I'll say, okay, distances equals transform, distance transform EDT, mask. And let me just show you what this image looks like. And what I'll do is I'll superimpose on top of this the stipple points, so we can have a look. Okay, so what this gives us by default is something called a distance image, as the name would suggest. What that is that's how far are you from the nearest, in this case, stipple point, whatever point you're indicating in this point collection. So you can see, like, these points here, or these pixels here, are pretty far. But then, close to the Voronoi, or close to the stipple points, you get much closer. Okay, so this seems correct. By the way, this is actually how people compute skeletons, something called the medial axis. You can see this is almost giving like a skeleton of the penguins, where the distance is really high. But anyway, I don't actually care about the distance. What I care about is which regions are closer to a particular stipple point than any other point. That information is computed as a side effect of computing this distance transform, right? We need to know which point it's closest to in order to know the distance to that point. So we can get this method to return. So I'll say return indices. You can see there's this parameter here. Return indices equals true. And so what this is going to do is actually return, so let me print the shape here so I can show you. This is actually going to return a 3-dimensional array, really two-dimensional arrays here. The first one is going to be the row of the nearest point, and the second one is going to be the column of the nearest point. That's actually a little bit annoying. I would prefer to just have a single index, right, of some point that I'm closest to in the stipple pattern. So let me do this classic trick where I convert. So I'll say, okay, we have our indices, so I'll say index row equals indices. That's going to be the first coordinate there, and then the column index, column equals indices 1. So these two images together give us the nearest location of a stipple point at every pixel. But I would like to encode that location as just a single number. So what I'll do is I'll do this classic trick where I say, okay, well, you know what? Indices equals index row times the number of columns in the image plus index column. And if you think about it, this is a unique unique map from some pixel location, row, column, to some number, I times columns plus j. Or so yeah, exactly, I times columns plus j. So anyway, I just make sure that I have a single number that's associated to each site. So now if I look at this, let's have a look at this image. This is now starting to look a lot more like that image I showed a moment ago when I was playing around here creating a Voronoi diagram. So telltale signs of Voronoi diagram is a bunch of convex polygons. You can see each polygon is centered at a site, although it's kind of hard to see. There's probably a lot of really small polygons around here because we got a lot of points. But anyway, okay, so that's cool. There's one more thing I want to do though, because if I look at these numbers, they're pretty big, right? Because they're potentially, there's going to be a unique number for every pixel location. So there's a lot of potential numbers that each of these stipple points could be associated to. I would like to remap them from 0 to the number of stipple points I have. So let me just say, I'll say unique indices equals empty indices. So I'll figure out, okay, how many unique numbers are there actually? Like if I look at this image, this Voronoi diagram, you see there's a lot of repeated numbers, right? These first 3 pixels are closest to the same site, which happens to be represented with a number that's 127,243. Okay, I would like, maybe that should be just number 0 or 1 or something. So what I'll do is I'll say actually indices equals, I'll say np.arange unique indices dot size. Or actually, here's what I'll do. I'll make a little, actually kind of like a numpy array, but I'll treat it like a method. I'll say index to index equals empty.zeros. I'll say, yeah, I'll say here, I guess indices dot size. Okay, and I'll say index to index np.arange. So let me actually, it'd be helpful here if I say the number of sites is equal to unique indices dot size. Okay, so for as many sites as there are, I want to set each. So I'm going to say, okay, indices, or I'll say unique indices. This is a little bit confusing. Just bear with me for a second. You'll see exactly where I'm going. This is equal to np.arange and sites. Okay. So what I've done here is made a little function that's going to map me to the numbers from 0 up to the number of sites minus 1. So I could do some numpy assignment here, and I can say, okay, indices equals index to index indices. Okay, and now you'll notice I get much smaller numbers, okay? That's all I was trying to do, just to make it a little bit easier so that I had contiguous numbers to refer to. 0, 1, 2, 3, 4. Not, 1, 2, 7, 2, 4, 3, jumping all over the place. I would like to have numbers in a sequence that are contiguous. So I got that now. Okay. Actually, let's look real quick. I requested 2,000 sites, right? In this example. Did I actually get 2,000 sites? That's a sanity check. And I didn't. I got 1990 sites. I got a little bit less. And so I want you to think for a second about the code that we wrote before and think, why is it that I might end up with fewer than I requested? And the reason is because we're drawing pixels at random here, but sometimes we might draw the same pixel more than once. And so clearly we have some collisions here. We've drawn a few pixels more than once. And so when we go to create this mask, those pixels come on top of each other and they only actually contribute a single stipple location. But you can fix that if you want. I'm just going to keep going because this is for artistic purposes and we don't need to be perfect. I think 1990 stipple points is close enough to 2000 that we're not going to notice the difference. So let's just keep going. Okay, great. So I have this image, this Voronoi image. Now what I need to do is compute the weighted average of each of these regions. And let me start off by doing this in kind of maybe a slow way, just to see if we get a good result, and then I'll think about how to speed it up. So what I'll do here is I need to do a weighted average of a bunch of sites. So what I'll do is let me initialize 2 arrays. Whenever you do a weighted average, you always need the numerator and you need the denominator. So the numerator here is going to be some sum of coordinate locations, some weighted sum of coordinate locations. So I'll say numerator. So I need as many of them as there are sites. Sorry, I use sites here. I probably should have said stipple points. Just bear with me. Sites, same thing as stipple point. I'm used to, now we're in Voronoi world, and in Voronoi world they're called sites. So I'm going to refer to stipple points as sites for a second. I'm sorry if that was confusing. Okay, anyway, so the numerator is going to be that. Denominator, and maybe make it a little clearer, I'll say weights. Because that's what the denominator is. That's the sum of the weights here. So I'll say np.zeros and sites. And so what I'm going to do, and this is where the loop is going to be slow if I do it in pure Python, I'm going to loop through each pixel and figure out which site it's associated to, and then do a weighted accumulated sum here. So I'll say for I in range indices.shape 0, for j in range indices.shape 1. Okay, so here's what I'm going to do. I'm going to say the numerator at location. Okay, so what do? We need to figure out which site this is associated to. So I'll say site index equals indices I j, right? So I'll say numerator site index plus equals. Okay, so what we're going to need here, we're going to accumulate this location, but it's weighted by the probability. So we're doing a weighted sum here. So what I did is I returned to the probability, you know, the thing that I was showing up here. I'm going to weight each pixel that belongs to a particular site by its probability. So if it has a low probability, its coordinate is not going to contribute as much to the weighted sum. So anyway, so the weight is going to be probability ij. So I'll say here, this is going to be, I'll call it just weight. This is going to be plus equals weight times that. And then we're going to say, okay, but we need to remember what was the total weight that we added to this particular site. Denominator. Oh, I called it weights. Let me keep changing my mind. I'll call it denominator. Okay. Denominator would be helpful if I spelled that right. Okay. Great. So let me run through this. Okay, site index. We're having a problem here. Oh, okay. I need to be careful when I'm doing this. I should really make sure that that these are ints because I'm using them as indices. Okay, so this took 2 seconds to do on this image. It's a little slow because I'm going to have to do it in a loop, but let's just see what we've got. So if I were to compute I'll say, you know, before I had rows and columns, I guess I'll say locations equals numerator over denominator. But denominator is a one-dimensional array, numerator is a two-dimensional array, so I got to make sure that I reshape the denominator to be a column vector so that this weighting gets broadcast to both the row and the column of the points I'm accumulating here. Okay. Now, actually, it did tell me there was a divide by 0 because sometimes there might be particular sites that don't have any pixels associated to them, so we wouldn't have accumulated any weight. So let's be a little bit careful about that. I'll say, maybe we'll just, yeah, so we're going to lose even more sites, okay? So, you know, I already lost 10 sites at the beginning when I drew them at the same place. I might lose some more, but let's just keep going and see what we end up with. So after this code runs, I'm going to say numerator equals numerator. Let me only keep the ones where the denominator is greater than 0. And similarly, let me only keep the ones where, yeah, in the denominator where the denominator is greater than 0. Run that again, and then we shouldn't get the divide by 0 error anymore. Let's see, how much do we have left? So we still have, okay, we only lost 1, actually. That's not too bad. All right. So yeah, let's go ahead and plot where did we show up here. So I want to do a similar thing where I say, okay, so locations, actually the second number is the column, the first number is the row. So where did I end up here? We are already looking at a lot better when you look at this, right? So give me a second. I actually want to make a little animation of this and show how these change over time. So I'm going to run this on a loop, and then I'll show you the result. Okay, I put this on a loop, and then I realized I had to be a little careful because this weighted sum does not necessarily give integer locations. These are going to be floating point numbers. So I ended up having to round them to the nearest integer so that they would be like what I did originally when I drew them at actual integer pixel locations. My whole code relies on that when I create this mask, right? These need to be integer indices. So anyway, I just did that, and then I made sure that I don't round actually up to the image boundary. Okay, so I had to do a little bit of annoying code there. So let's have a look at what the algorithm did. So here's my initial set of points here. And as I proceed through my iterations, here, hang on a second, let me actually make this a little bigger so you can see it better. Because it's pretty cool. So let's go ahead and blow this up. Okay, so there's the initial, right, that I get from just randomly choosing coordinate probabilities. First iteration, I'm already looking a lot better, right? These are looking more evenly distributed. And as I keep going, it gets better and better and better. And actually, there's something interesting that happens. That you notice these points on the side here, they start to migrate down. If I zoom in, we start to get, this point here is going to end up, I think, on the penguin, actually, by the end, yeah. That's actually going to help us when we do the traveling salesperson, because we're going to get, we're going to be able to connect the penguins better and actually fill in their boundary here. That's what I suspect as we continue. So it really helps to do that weighted average, where where they're ending up on these darker regions and distributing themselves evenly throughout them. Okay, now give me a second. I'm gonna fix my screen here, and then we can continue and actually start talking about the traveling salesperson part. Oh, actually, there's one more thing I want to do, because it's gonna actually come in handy later also. So I want to use something called numba. My students used to laugh at this name, numba. I want to use numba just-in-time compiler to speed this up, because these loops in Python are going to be really slow unless they get compiled in, on the fly into C code. So let me actually, let me take this code, what happens in the loop here, and actually, I guess I'll start. Okay, here, this stuff is okay because it's been vectorized into numpy, but this stuff is going to be slower. So let me take all of this and put it in a little helper method. So I'll call this def do Voronoi iteration. So let's see. So what I need here is, okay, the number of sites. I need my indices. I need my probability. And that's probably good. And so then I'll return here the rows and the columns that I get after that. And so the magic incantation here is JIT no Python equals true. And I'm probably going to have to mess with this a little bit. I'm admittedly not an expert with numba, but I can get by. So let's just see what I can do here. This was for the animation. I guess I'll keep it here for now. Although, no, let me get rid of it. It's fine. Okay, so let's try to call this method now. So I'll say, instead of what was there before, I'm going to say update the rows and columns to be do Voronoi iteration. Else is probably not going to work. Let's see. Okay, so it's complaining here. It's saying invalid use of bound function. Okay, so what is that? Is that this? Let's see. Nope, it's still giving me that. Let's see, where's it happening? Rows, columns, give me a second, I'm going to clean this up and I'll tell you what it was. Okay, so I realized what the problem is. Numba did not like me using the as type int in here. I had this. Okay, that was actually pretty easy to fix. Usually it's a lot more work to figure out what I'm using in Numba that I shouldn't be. But in this case, all I had to do was just move that as type int out of here. So it's returning floats, whatever, I don't care. So yeah, this is way faster. This took 1.3 seconds for 10 iterations of this. I'll just show you run it again. One thing you'll see is often the first time that you run this, numba will be a little bit slower because it has to compile this code. But then subsequent times that you run it, it'll be faster. So I think the first time around it took like closer to 3 seconds because it had to compile on the first loop. It had to actually compile this method. Okay, but anyway, so that is that. It's a great trick to help make things faster. And to write, sometimes it's clearer to write code using loops than it is to do the numpy vectorization. I mean, this code was a little bit messy. I did it without loops, but sometimes you just want to use the loops. Use numba. It's okay. All right, so I had to go away and do my day job, but now I'm back and I'm ready to finish this video. So what I did is I organized everything we just did with the stipple pattern actually wrapped it into the stipple method with a couple helper methods. So I got this refined stipple, which does those Voronoi iterations in a loop, and then I have the helper method that uses numba to actually do individual Voronoi iteration. Okay, so now what I'm ready to do is take these stipple points and connect them together with a traveling salesperson loop. So I'm not going to be able to go through all the theory in this video, otherwise it'll take forever, but I have a couple other videos that I made for my data structures class back in the day where I talk about how one way that you can get a traveling salesperson loop is to create the Euclidean minimum spanning tree of the set of points, and then to do a depth first search traversal. So I do that and actually prove that here in this video, so I'll link to that. And then actually in the next video I show that in order to get a Euclidean minimum spanning tree efficiently, it's actually good to do what's called a Delaunay triangulation of the point cloud in 2D. So to do, in this case, the Delaunay triangulation of the stipple pattern, and just use the edges in that graph, in that triangulation, as the starting point for a minimum spanning tree. So that I'm going to do here, because otherwise what I have to do is compute all pairwise distances between every single point in this stipple. So if I have 2,000 points, I'm going to need a 2,000 by 2,000 matrix. That's okay, but let's say I have 10,000 points. Now I'm starting to get into trouble. A 10,000 by 10,000 matrix, and it only gets worse. That'll scale quadratically. Whereas the Delaunay triangulation, if I only look at the distances between points that are connected by edges here, I only have to consider a linear number of edges in the number of stipple points. And then I'll compute the minimum spanning tree of those. Now, I guess I won't give away the whole assignment that I had, and in the interest of time, I'm not going to implement the minimum spanning tree from scratch. So that's something that I walked my students through in my data structures class that they would do. But actually, I'm going to make use of another scipy method here in the sparse library to create a minimum spanning tree. So that's the game plan. I need to construct this graph from the Delaunay triangulation, and then I need to compute a minimum spanning tree, and then I need to do depth first search. Okay, so I have those 3 steps down here. Let's knock them out one by one. So for the Delaunay triangulation, we're once again going to turn to scipy. Scipy has an awesome library called Delaunay, and I can use that to compute the Delaunay triangulation. By the way, the Delaunay triangulation is actually the dual of the Voronoi diagram, the thing that we use to do the stipple refinements. So that's kind of cool. So the two are related to each other. So maybe I could have stored it there, but whatever. I'm just going to compute it again here. So let's go ahead and do that. So I'll say, okay, so this requires a point cloud represented as a 2-dimensional array, where the first column is the x-coordinate and the second column is the y-coordinate. I can make either the rows or the columns be the x or y-coordinate. That won't affect the triangles that I get in the Delaunay triangulation. It won't affect the topology. So I can do whichever one I want. So I'll say here, triangulation equals Delaunay. And I guess I'll put the rows first in my little point cloud. This actually will put the rows along the rows in the first row and the columns along the second row. I need to transpose this, so what it's going to be, row, it's going to be like x1, y1, x2, y2, x3, y3. That's what I want the array to look like. That's representing my point cloud. So I give the Delaunay triangulation a bunch of points. And then what it gives me back, actually, is something, they call them simplices. There's a more general notion. You can go do this in higher dimensions. In 2 dimensions, a simplex is a triangle. So it's going to give me these things called simplices. So if I look at that, whoop. Okay, I actually need to import this up top. So if I look at the simplices, here they are. So these are the indices of triples of stipple points that are all connected to make the triangles in the Delaunay triangulation. In order to do the minimum spanning tree, I need to actually extract a list of edges. So each triangle gives me 3 edges, although each edge is shared among up to 2 different triangles. So what I should do actually is make a set of edges, and I'll iterate through the triangles here. So I'll say for try and try, and let me go through the 3 edges in each triangle, and I'll add them to the set. And I guess I'll add them in both directions. So I'll say here, yeah, because, okay, yeah, let's go ahead. So I'll say for I in range 3, and I'll say E1, E2, so I'm just going to unpack here. I'll say try at index I, and then try at index I plus 1 mod 3. Because what I want to do here is get, index 0, 1, index 1, 2, and index 2, 0. Those are going to be the edges on the triangle. To loop around the triangle, I actually have to connect the last edge to the last vertex to the first vertex. Again. So this is going to get me the 3 edges on the triangle. And then what I'll do is I'll say edges dot add. I'll say E1, E2, and then I'll also add that edge going the other way around. E2, E1. So in this example, that would add edge 525, 539, but it would also add edge 539 and 525. Then it would add this pair, 539, 486 in the other one, and then 486 and 525 would be in there. And I'm using a set because I know that I might see these edges again from another triangle on the other side. All right, if I look at this triangulation, like this edge here actually is involved in 2 different triangles, this one up here and this one down here. So I was just set so that I don't accidentally count them twice. But at the end, I'll maybe put it back into a list again. Okay, to make sure this worked properly, let me go ahead and plot this. There's going to be a lot of edges involved, but actually a linear number. So not, luckily not 2000 choose 2. It's going to be on the order of, well, I have to remember Euler characters exactly, but on the order of 2000, which is a lot better. So anyway, let's go ahead and plot these. So I'll say plt.scatter, columns, rows. And let me iterate through these. So I'll say for I1, or I'll say maybe, yeah, for ij in edges. Yeah, I'll probably draw most of the edges twice here, but that's okay. Or I'll draw all the edges twice because they're going both ways, but that's okay. Let's just to see if this looks right. So I'll say here plt.plot. What we want here is the rows, and then the column. Well, actually, I'm plotting the columns first. Okay, columns, ij, and then rows, ij. And this should look pretty nice. It's going to take a second because this loop here is very slow. Okay, but anyway, oh, and it drew them upside down because of the way the rows and the column. Yeah, the rows actually start indexed at 0 here. But anyway, yeah, this looks right. There's a lot of little triangles in this, and some big triangles that are filling in these gaping holes in my stipple pattern. Okay, yeah, but that looks good. And also, it's very colorful because since I'm drawing each edge independently here, matplotlib cycles through these colors. So that's nice. And when I was teaching data structures, I found this sort of thing to be really helpful. At first, it seems like maybe it's a nuisance. Oh, I don't want these all to be different colors. But I find that it gives the brain, for those who can perceive color, it gives the brain something else to latch onto when I'm giving different examples. So I use these when we were drawing trees and all sorts of other things. Anyway, that was me reminiscing, trip down memory lane there. But okay, so I think we've got the list of edges. What we need to do now is construct this minimum spanning tree. And in order to do that, I need to construct a sparse matrix that is what's known as an adjacency matrix, or a weighted adjacency matrix, where each entry in the matrix holds a distance between two vertices on either side of an edge that's actually in the matrix. So most of the edges between vertices here we're never going to consider. Like this vertex is not connected to this vertex over here. So we don't need to compute a distance between those two. But we will need to compute distances between all vertices that are connected by an edge. So to accomplish this, what we should do is construct a vector between the vertices on either side of each edge. And actually, this is going to get kind of annoying if I don't take this out and make it its own point cloud. So I'll call this stipple PC, that point cloud here is equal to that. And actually, the other thing I'm going to do is I'm going to turn this edges into a proper numpy array so I can use it to index to make my code really nice. Okay, so what I'm going to do is take a vector between the endpoints on either side of each edge. So that'll be stipple, point cloud, edges. So, you know, it doesn't really matter which direction I put it, but I'll say, you know, the second endpoint minus the first endpoint. So this is a vector between each edge endpoint. Let's go ahead and make sure I got this right. And actually I can see this is how many edges I have. It counts them twice though, which actually will be convenient in code. So I have about 3 times as many edges as vertices. And that actually matches from Euler's formula. So that's cool. Now what we need to do is turn this into a sparse matrix, because that is what the minimum spanning tree expects. So a sparse matrix is a matrix or a 2-dimensional array where you only store the entries that you're actually using, or the entries that are non-zero. So I am going to use that library. So it's actually in scipy again. Scipy.import sparse. And what I have to do is just tell it. So I'm going to make this thing I'll call it adjacency, my adjacency matrix. So what I have to tell it is, okay, first of all, what are the values that I'm going to use in each row? And actually those are going to be the Euclidean distance. So I need to compute the length of each of these vectors. So let me do that real quick. So I'll say distances equals, so it'll be the sum of the squares of the differences of the components. This is just the Pythagorean theorem. So that's going to be dv squared axis equals 1. So I'll have a distance associated to each edge. Actually, this is the squared distance. Let me make sure that I take the square root. And also let me make sure, this probably won't happen, especially because I took them at unique pixels, but just in case numerically I end up with a squared distance of less than 0, I'll clamp it there. And then I'll say distances equals the square root of distances squared. Okay, anyway, great. So this is the value that I want to have at each non-zero entry in my matrix. So I'll say here this is distances. And I want the row to be, you know, the first edge that I took, the index of the first vertex on the edge. And I want the column to be the index of the second vertex on the edge. So I have a video where I talk about adjacency matrices. I'll link to that video so you can get more information if you'd like to understand a little bit more about these matrices. But for now, just know this is an encoding that this library expects. It's just another way to represent the edges and the distances associated to them without blowing up memory. So we're going to have a 2-dimensional array which has as many rows and columns as there are points. So I'll say n stipple here. That's the number of rows or columns in this 1984, that special number. And so yeah, eventually I have to say, okay, yeah, this is a 2-dimensional array, or a sparse 2-dimensional array that has that many rows and that many columns. But most of the rows and columns, or most of the entries are going to be 0, so I'm not going to store them explicitly. I'm only going to store the entries where I need them, which is going to be on either a row corresponding to the first endpoint and a column corresponding to the second endpoint. And this matrix is symmetric, so if there's an entry in ij, I want the same entry to be in ji, but I double counted the edges, so I already get that for free. And there we go. Okay, this is the adjacency matrix. If I print this, you can basically see it's almost like a hash table, where you're only storing the entries that you actually need. All right. Well, this is exactly what we need from this library here. So let me import this, and actually I've never used this library before, so we'll be going through this together. I've always done this myself, but yeah, let's just see what it looks like. Actually, it looks like it's going to also return a sparse matrix, just like the one we input, and then we'll just see what rows and columns we actually have that belong to the tree. So let me go ahead and import this here. So I'll say from scipy.sparse.csgraph import the minimum spanning tree. And let's try this out. So I'll say mst equals minimum spanning tree adjacency. That was really fast. That's cool. So let's look at it. Again, it's a sparse matrix. So actually, let's see. I think I have to say 2CO matrix. Somebody who's watching this can correct me if I'm wrong. MST dot 2. Oh yeah, I have to say 2CO. And then I'll say MST dot rows. Nope, still doesn't work. Row? Yes. Okay, good. I got it. So actually, what this is going to give me now are I should be careful what I call these, but these are going to be the edges in the MST. So maybe we'll say edges MST equals array. Okay, so whatever rows and columns are actually involved in this MST. So that'll be MST.row, MST.col. So what did I do here? This was just to, I don't think it'll work without this line here. Well, I'll try it again, but yeah, I need to convert it into a format where I can extract the non-zero rows and columns. Okay, anyway, so now I have a different list. So let's look, so the original number of edges, and let's look at how many edges I end up with in the minimum spanning tree, and then I'll plot them in a second to see what it looks like. Okay, so, oh, interesting, I forgot to transpose this. Okay, let's just keep it consistent here. Okay, so this should make sense. In fact, let me see. Yeah, so first of all, I have many fewer edges in the minimum spanning tree than I do in the original Delaunay Triangulation. Now, one thing that's a little interesting, I should have, if it's truly a tree on 1984 vertices, I should have 1983 edges. So that's a little weird that I have a little more than that. So I do want to be a little bit careful about that. Let me check again. Maybe there was something wrong with the way I indexed the edges. Let me see. So if I print mp.unique edges, so the original edges that I put into this, there were 1989. Okay, hang on. Something's a little weird here. Why would there be 1989? I'm going to crunch on this for a second. But at least that makes sense. Okay, if there were 1989 unique vertex indices in this matrix, then it makes sense that I would get back 1988 edges. There's always one fewer edge in a tree than there are vertices. But let me just double check anything, because I thought, let me see, end stipple here. Oh, you know what? I might have generated the stipple pattern again. I think we're good. I think I generated the stipple pattern again in between. I stopped my video for a second. I think I generated the stipple pattern again, and it's a little bit random. I didn't seed it. Okay, so I actually have 1989 stipple points. Okay, so we're out of 1984 land. Okay, anyway, so everything adds up. Le compte est bon, as the French would say. So I have 1988 edges associated with my 1989 stipple points. And that is my minimum spanning tree. So let's just go ahead and plot that again, just like I had before. So I'll say plt.scatter columns, rows. It's going to put it upside down, but whatever. This is just for visualization. And let me go and loop through these edges. So I'll say for ij in edges mst. And I'll say plt.plot columns ij, rows ij. Okay, there we go. So there's a minimum spanning tree. So this is actually a tree. And, okay, this is starting to get kind of annoying. Let me just, I forget how to do this. Let's see, gca.reverse, no, reverse, y-axis. Something like that, I don't remember. Another thing I can do, okay, just since I'm recording this, I don't want to do this again. Another thing I can do is I can just plot the negative y coordinate. Okay. Okay, so this is showing the right way up. So anyway, this is already kind of cool. This is a minimum spanning tree between all these vertices, and this is already like kind of artsy, right? But what I want to do is connect up these edges in a loop. Okay, and so that's where step 3 comes in, which is we need to do a depth first search through this. And keep track of the order in which the vertices are visited in that depth first search, starting at some point in this stipple pattern. Okay, so in order to do depth first search, I need to represent my tree as a graph so that I know which edges are coming out of each vertex. So I need to change this representation that I have a little bit. Really what I need is just a vertex neighbor adjacency structure. So I'll set up vertex neighbor adjacency structure. And so I'll say vertex neighbors. I can get away with the dictionary here. So I'll say for ij in edges mst. I'll say if not I in vertex neighbors. We'll make the vertex neighbors at I be an empty list. And let me see, would I ever need to, should this be a set? No, I think I'm okay with just a list. All right, and then I would say vertex neighbors j, same thing for j here. Not j in vertex neighbors. And then I'm just going to say vertex neighbors, I mean, I might as well make it a set just to be safe. I really don't care what the order of them is, actually. So I'll just do that. But then I'll say vertex neighbors I.add j and vertex neighbors j.add I. So this is an undirected graph, so these are mutual neighbors of each other. That runs very quickly. And now depth first search is just actually just a really all I got to do is put these things on a stack and keep track of them. So yeah, once again, I have a video going over depth first search. I can link that. I've got all sorts of these videos, but I'll just do it here without too much explanation. I'm going to use something called a frontier as my stack. So this is a stack representing vertices that are on fire, I'd like to say. So these are vertices that I am visiting, but they haven't been visited yet. So I might as well start off visiting vertex at index 0. And so as long as I have stuff that's still on fire, I have to keep going. And let me also keep track of what has been visited so far. And then I'll keep track of the order in which they are popped off of this stack or frontier. So here I'm going to say, my vertex equals, or vertex index, just to be very clear, is equal to frontier dot pop. So I'll take off whatever is off the back of the frontier. That's what makes this depth first search. If I were to change this to pop front, it would be breadth first search, but we actually want depth first search here, DFS. Okay, and then what I'll do is I'll say visited.add vertex index. So we've now visited this. So now it's not on fire, it's burned to the ground. That's the analogy I like to use. So it's off of the frontier. So we can add it to the order. And then let's keep that. Keep track of that. So also order dot append vertex index. And then I will say, okay, now I need to look at the neighbor. So I'll say for neighbor index in vertex neighbors, vertex index. Okay, so I have my neighbor index. And so if this, let's see, I guess I'll also have another set here. I'll say on frontier. And so yeah, let me also make sure that 0 starts off in there. Yeah, so I'll say when the thing comes off of the frontier, I need to make sure that I update this. I'll say on frontier dot remove vertex index. Okay, so basically I'm going to add a neighbor if it's not. I'm going to add a neighbor to the frontier if it's not already on the frontier and if it hasn't been visited. So I'll say if not neighbor index in on frontier. That looks a little weird. In on frontier, whatever. And not neighbor index in visited. Okay, so if that's the case, then I want to actually add this neighbor to the frontier. So okay, I set you on fire. You're a neighbor of mine. I'm going to set you on fire. So then I'll say frontier dot pen neighbor index, and then I'll say on frontier dot add neighbor index. Okay, so that ran very quickly. And so my claim is that if I plot a line connecting all these vertices, so I'll scatter these again. But now if I actually reorder these vertices in a special way, according to this order, then I should be able to connect them in a loop. And that loop is an approximation of the traveling salesperson. Actually, I mean, yeah, I'm going to get a loop. The claim about using depth first search specifically is that the loop I get does not exceed, the edges along the loop that I get do not exceed twice the length of an optimal traveling salesperson loop through all the vertices. So this is not going to be twice as worse. So if these were a bunch of cities that I was driving between, and the loop that I get here took 2,000 miles, then I know that the best I can do is not any better than 1,000 miles. That's the guarantee I get from the depth first search. Well, let's see what that actually looks like. So if I were to use this order, so once again I'll convert it into a numpy array so I can use it to index. So I'll say vertices order equals what I call my point cloud here. I called it stipple PC. Or maybe I'll call it, yes, stipple order. So yeah, let me go through them in that order. Actually, there's one sneaky thing I want to do here. I want to, so that it makes a loop, I want to add the, what's actually the last, oh no, sorry, I want to add the first vertex at the end. So let's say that this happened to go through, just a toy example, let's say I only had 4 vertices. So let's say 1, 3, 2, 0 or something, right? So let's say it went through these 4 vertices in that order. Then I want to tack on 1 at the end so that it loops back around. 1, 3, 2, 0, back to 1. Okay, because I want to actually plot this in a loop. Okay, and actually just so I'm consistent here, let me order, let me reverse the y-axis again. Oh, whoops, I forgot. Okay, this is the x-coordinate, this is the y-coordinate. Okay, anyway, so, all right, let's draw that path now. So basically I just copy this code, but I'm going to now use a line segment to connect these adjacent points instead of. Okay, so there we go. There's our traveling salesperson loop. So this is a loop that's connected on the vertices. Actually, it's not bad. So you can see, like, you know, it's not jumping all over the place. So it's like, if I'm at this city, if this is like a traveling salesperson, it makes more sense for me to visit the city right next to it than to jump all the way over here and then jump back and then, right? Just to show you by contrast, if I were to make this some random order, so if I were to say order equals mp.random.permutation length, or n stipple, I'll ignore the loop for now, but you'll see. So Yeah, so this is just going in some random order. It's just totally awful. Okay. So just to say, why do we go through all this trouble with the getting the Delaunay Triangulation, getting the minimum spanning tree, doing depth first search on the minimum spanning tree? It's because we start off with a very nice order. And again, we know that the length of this entire cycle doesn't exceed twice the length. I proved this in my other video. It doesn't exceed twice the length of the best that you could possibly do. Okay. But we're not completely done. We're very close. But you notice this has some properties that make it really not very aesthetically pleasing. Actually, it's not bad. It's not bad. But you notice that it crosses itself in some places. Like that's not so nice. And in fact, what you can show, if I go back to my little video series here, I had another video where I talked about if you have a traveling salesperson order and you find that there's a crossing, you can always do better. Just by some basic, well, assuming that this is in a metric space, or that this graph satisfies what's known as the triangle equality. If you have a crossing, you can always come up with a traveling salesperson loop that is a lower overall distance if you get rid of that crossing. And also, for us, we don't really necessarily care about the length so much. But what we care about is this visual property. We want to identify and get rid of these crossings anyway. So not only is the traveling salesperson loop going to get a little tighter, a little smaller, but we're also going to have that property that we want. Okay, better sketch this out because this is a little tricky. So a crossing happens when we're at a particular vertex I, and we go to vertex I plus 1 in the path. But somewhere else in the path, there's a vertex j. And so, this could be later, or it could actually be before. And when j goes to j plus 1, it actually crosses over the line from I to I plus 1. And if that's the case, we can always do better. I proved that in the other video. It's just a simple use of the triangle inequality. But so what we want to do is change this, up to this point here. And actually we can assume, what we'll assume is that I is less than j without loss of generality because, if we find a crossing here, it's also going to exist here. Well, that'll cover everything. So if that's the case, what we're saying is, okay, we had all the vertices from 0 up to index, so 0, 1 up to index I. Well, we should carefully deal with some edge cases, but yeah, 0 up to some index I, and then we had I plus 1 up to index j. So it looks like this. It's like I go up to I, and then I go to I plus 1. I go over and do a bunch of things. And I come back here. Ooh, hang on a second. Yeah, so I do a whole bunch of things. I come back here, and then I go to j plus 1, and this makes a whole big loop, and then end up back here at the beginning. But what I want to do instead is splice this out so that instead of going from I to I plus 1, I actually go from I to j. Give me a little dotted lines here to show this is what I am going to switch to. And then that means that I have to route from later on, route from I plus 1 to j plus 1 instead. Okay, so let's carefully look at what that does to the array. So I'm saying here, all right, the array used to be in the pieces, here, I'll say n minus 1 here for n vertices. So we used to have the array in the pieces 0, 1 up to I, and then I plus 1 up to j, and then j plus 1 up to n minus 1. So that's before. But after, we want to change this so that we start off the same way, but we reroute in the middle. So we're going to go 0 up to I. But then we're going to have this chunk actually in reverse. I'm going to go j minus 1, right? So the one that comes right before j would be j minus 1. So in the original path, I went around like this. But now I'm actually going to go around like this. So to go in the opposite direction. Okay. So that'll be, yeah, j minus 1 down to I plus 1. And then we can continue as normal. So it's just actually this middle segment here that needs to be switched around. All right, so let's see if we could do that in code. I'm going to keep this picture here because it'll help me. So what I have to do is search for an index where this crossing happens. Alright, so I'll just set up a nested for loop that keeps I less than j. So we have to see how many, we have this array order, that's what holds the indices that we're going to change the indices in order around. It's confusing. We're going to change a permutation of a permutation that's already there. But yeah, let me change these elements. So what I'm going to look for here is, okay, so I'm going to look for I in range. So I'll say big N here. I'll use the same variable used here. That's the number of points. I think I probably had another variable for that at some place up here, and I already forgot because this video is getting so long. Let's just redefine it down here. So I'll say len order. Like for I in range N, for j in range I plus 1 N. Okay, so what I need to do in order to identify crossing is actually compute the lengths of these segments here. So actually, let me label these segments in the image here because that'll help me a little bit. I'll call this segment A here. I'll call this segment B. I'll call this segment C, and I'll call this segment D. So let me go and compute those lengths there. So A is going to be the segment between I and J. So what I'll do here is say, okay, I need a vector length. So I'll say, make a little helper method here. I'll say get distance between, so I'll say order I, j, and I need to refer back to the original point cloud, stipple point cloud. So here I'll say I got to construct a vector between these 2 points. So that'll be stipple point cloud and index j minus stipple point cloud and index I. I'll just sum the square differences. And then I'll take the square root of that. So I'll say square root. Actually, I'll just say if dist is less than 0, this could happen because of numerical problems. I'll just return 0. Otherwise, I'll return square root of dist. Okay. So, oh, whoops, I meant to say order. See, here's where my editor helped me. I didn't use the variable order there. So it graded out. I'm going in the order that I started with here. So I need to use that to index where I am in the point cloud. That part's a little bit confusing, I apologize. But okay. So let's do it. So I'll say A is get distance between I and J. Let's just make sure this runs real quick. It's going to do a nested loop, so it's going to be slow. We'll speed this up later using our favorite trick with numba. But now, okay, yeah, this is going to take a really long time if we actually do it in pure Python, and we don't do early abandoning. So I'll show you in a moment. As soon as we find one, we're going to break out of this loop because, you know, we're going to fix that, and that will, you know, could introduce other crossings that we need to change. Okay, let's keep going here. If I do B, I'm going to need to look at the distance between I plus 1 and j plus 1. And now I'm realizing I better make sure those aren't out of bounds, so let me do the loop like this. Yeah, actually I might need to be a little careful because this could loop around, but I'll keep it simple for now and just do it like this. Okay, so that gives me A and B. And C and D, are going to be, I mean, the code is very similar. That's why I made this helper method. So C is going to be between I and I plus 1. And then D is going to be, whoops, D is going to be between J and J plus 1. And so, okay, so now what I got to do is say, look, there's a crossing if A plus B is less than C plus D. That means I can do better by rerouting. So I'll say if A plus B is less than C plus D, then that's a crossing. And so, actually, what I should probably do here is make a little helper method. So here I'll say def get crossing indices. So I'll pass along order and stipple. And so what I can do is just return out of this method. So this is going to be early abandoning here. Okay, so we're going to break out of this a little bit early if we find a crossing. So yeah, let's see how long that takes. And you know what? I'll double check and see if this is actually a crossing. I'll plot this here and we'll see if it looks like it's a crossing. So yeah, we'll scatter that stipple and plot the stipple. And let's get, I'll say here, ij equals get crossing indices order stipple PC. Okay, now this went faster because it found one pretty quickly. So it's telling me that at indices, okay, so yeah, pretty early on, I at index 2, J at index 1949. Okay, let's see, let's have a look at that. So if I were to plot a stipple pattern, but let's plot those indices there. So here I'll say stipple PC. I'll look from I to I plus 1. And then I'll look from J to J plus 1. So I got to plot the x coordinates and the y coordinates. So look in I to I plus 1. And, x and y coordinate there, and then J to J plus 1. Let's see if we can identify the crossing. And let me also draw these in red so they stand out. Yep. Well, actually, a couple things. Once again, I need to use order. Oh, no. A stipple PC has been reordered. Okay, this should be stipple order. Here, there we go. I'll come back to this picture in a second, but okay, let's see. It was complaining here. 3 indices were, okay. Yeah, I was trying to take out just coordinate 0 here. Give me a second, I'll get this plotted. Okay, let's keep going here. If I do B, I'm going to need to look at the distance between I plus 1 and J plus 1. And now I'm realizing I better make sure those aren't out of bounds, so let me do the loop like this. Yeah, actually I might need to be a little careful because this could loop around, but I'll keep it simple for now and just do it like this. Okay, so that gives me A and B, and C and D are going to be, I mean, the code is very similar. That's why I made this helper method. So C is going to be between I and I plus 1, and then D is going to be, whoops, D is going to be between J and J plus 1. And so, okay, so now what I got to do is say, look, there's a crossing if A plus B is less than C plus D. That means I can do better by rerouting. So I'll say if A plus B is less than C plus D, then that's a crossing. And so, actually, what I should probably do here is make a little helper method. So here I'll say def get crossing indices. So I'll pass along order and stipple. And so what I can do is just return out of this method. So this is going to be early abandoning here. Okay, so we're going to break out of this a little bit early if we find a crossing. Okay, so if I call this method, let's see what I get. So I'll say here ij equals that. I'll print ij. You notice it goes much faster because actually it finds one pretty quickly with I equals 2. Now give me a second, I'm going to make some code. I'll plot this because I want to check to make sure that this is actually a crossing on the stipple pattern. So I'll set up some code to do that. Okay, I just plotted the result and I noticed something pretty interesting. So when I zoom in, I'm trying to look at these segments. You know, I'm thinking I'm looking at a segment like this going from I to I plus 1 and a segment going from j to j plus 1 that cross each other. What I actually found was, so okay, I'm drawing, let me actually make the colors corresponding here. So I was drawing these in red, and I'm drawing the other ones in green. Okay. What I actually found was they didn't cross each other. So these two red segments didn't cross each other. But the sum of them was just slightly less than if I had changed the order. So I printed up here, it's like A plus B was 24.8, C plus D was 25.8. So if they cross, then A plus B will be less than C plus D, but it's not an only if. This can happen other times. Then you know what? When we do the swap, the path is going to get shorter. So in the traveling salesperson problem, we're always trying to get the shortest path. So we might as well swap those anyway. Okay, that's cool. So yeah, let's try to swap them, and then we'll run it again and see what we find the next time. So looking back at my little guide here, let me put this on the bottom here so we can look at it. So what I'm supposed to do is, once I figure out what I and j are, I need to change this array so that I splice out. So I'll say order equals order up to and including I. So for my slicing notation, that's actually 0 to I plus 1. And let's see, you got to be careful. Order is a numpy array, right? So yeah, so I better use concatenate here. So what I'm going to say here is concatenate. Okay, and then the tricky part is in the middle, from I plus 1 to j, that needs to go in reverse, right? Okay, so let's first try to get, so from I plus 1 to j would be this, but I want this to go in the reverse order. So for me, the easiest thing is just to do that. Okay. So that would go, so yeah, it's tricky because I is less than j here. So we start at I plus 1, and then we go up to, but not including the last slice index. So that's up to j, and then we reverse, and that should do it. Okay, and then finally, we're going to go from j plus 1 to whatever's left. And that should be it. Okay. So yeah, this is going to be a little bit messy in the notebook, but I can run this a few times and sort of see how the answer changes. So yeah, after I do this fix, I'm going to get a different answer. So I still get 2 in 1949, but now if I run this again, I actually get 0 in 1949. So there was a different crossing that got identified there. So yeah, let's see where that one showed up. Or actually, I should be careful here. Let me not, okay, I'll run this again, but let me not do the change. So this is changing. Okay, now I found one in 518. This one looks like a much bigger difference. Let's see this one. So this order is changing, right? It's going through the vertices in a different order. So let's have a look here, kind of see where that crossing was. Okay, so let me zoom in here between 200 and 300 again, and then yeah, actually these bounds will work. Oh, weird. Okay, so something is, it's weird that I'm not getting a crossing still. let me take those away real quick and just make sure that, or let me draw those as dotted lines. And we'll make sure that it's actually doing this in the right place. So, okay, it's going to, yeah, and let's look before and after. So let me just make sure this is doing that crossing properly. So if I were to change this and then look at this again, let's make sure that this is actually showing up in the right place. Okay, and let me zoom in there. Just want to make sure it was still a traveling salesperson path. Okay, let's look. Let me get rid of this and let's look before and after. Matter of fact, I'm going to do this in a loop, and we're going to see what happens every time this changes. So this loop is going to be a little bit slow at first, but it'll be fast enough for us to look at an animation. So what I can do is, basically just keep doing this in a loop, and every time I'm going to make a plot like this. Actually, you know what? We'll probably be able to see it happening, so I'm not even going to bother highlighting this that way. So let's just do this in a loop. And so, for some number of iterations, I'll just do this. I'll say for, let's do this maybe 100 times. Or I'll just say IT in range 100, and let's do this. So let's make a figure. So here I'm showing you my debugging process. And every time I will clear this and plot this over again after I've changed this crossing. And then I'll save. I'll say, okay, let's try this. Let's run this. It's going to run. It's finding a different one each time. Let's have a look at what they look like. So I'm going to pull this up here. Okay, so actually, okay, cool. That looks pretty good at the beginning there. You see how there was a crossing there and now there's not? It got straighter. Okay, this looks like it's working. Look at that. See how it's undoing the crossings there? Oh yeah, that was a really good change. Okay. So yeah, it's not always just getting rid of a crossing, I guess, but every time the path gets a little bit shorter. Yeah, that wasn't a crossing, but it helps the path to get shorter, and somehow it looks a little bit better each time. And so what I need to do now, this is really slow actually, because I want to run this like a bunch of times. The time complexity of a single iteration is n squared right now because I'm doing this nested loop, although I'm doing early abandoning, so that helps. But since I've already done this above, maybe I'll take this offline and I'm going to try to improve this using numba. I did this further up here when I was doing the Voronoi iterations. Remember, we used numba. So I'm going to do a similar thing, try to speed this up, and I'll let you know how it goes. So let me do that real quick. Okay, so it wasn't too bad to get this in numba. I had to get rid of the helper method. I don't know, maybe some of you out there are better at number than me, but that's what I had to do to get this to work. But yeah, it's fine. It's a lot faster. If I run it, it takes, about 10 seconds to go through 100 iterations. It's a little bit slow though, and I still want to make this faster. So there's something I can notice. Okay, so maybe a little more than 10 seconds for 100 iterations. One thing that I'm noticing about the I and the J that it's finding is they're generally like increasing. So you can see I is going up in lexicographic order, IJ, they're basically increasing. Not always, you see this one went down there. But so what the result is, it's taking longer and longer to find the next crossing because it has to start at the beginning and search each time. What we can do is just pick up where we left off. So maybe I'll say in this loop, I'll have some variable called I last, and I'll make I last be I. and I'll pass that along here. This is all, this is like a heuristic. I'm not trying to get a perfect optimization here. This is already very greedy what I'm doing. I'm just like, find the first one you can. Or I guess not greedy, but almost like arbitrary, right? Like find the first crossing that you can and get rid of it and then look again. I'm sure you could be much more clever about where you looked for the crossing, but I'm just going to do something simple here. And so what I'll do is I'll say, all right, I'll pick up where I left off, and actually just to make sure that I'm, I can keep going. Let me loop around back at the beginning. 0 to I last. Yeah, let's try that and see if it goes any faster. So make sure I'm passing I last along. So it's like, okay, if I found a crossing or they're not crossings, but if I found an improvement, not necessarily crossings, if I found an improvement at I is equal to 376, I'll pick up there again next time. Let's see. Here's numba again. It's saying nothing found for signature add. Oh, okay, it doesn't like the range that I'm doing here. Adding the ranges together. Let's see if I could do... So I'll show you one gory numba thing and then we can move on. Maybe I can do, let's see. Well, let me add list. Let's see. Maybe it's because these are generators. It doesn't like that. Range is actually a generator. Okay, yeah, that worked. Oh, wow. Yeah, look how much faster that was. Yeah, just picking up where it left off. Because, it would get worse and worse. It's like, okay, I left off at 300 last time. I got to go through 300 again until I get there. I left off at 301 next time. Okay, it compounds. It's like that quadratic compounding. Okay, yeah, so that was way better. So let me run this. I'm going to make a much longer animation. I could run this until I don't see an improvement anymore. And then I know that there's no crossings. So I guess, yeah, if I return none from this, I think that should happen by default. But I'll say result is equal to that. I'll say if result is none, then I'll break. Otherwise, I'll say unpack this ij equals result. So I could actually go forever. I could say while true, right, until it breaks. But probably it's a little bit wiser if I cap it at some maximum number of iterations and see how it goes. So let me do that. I'm going to make this little animation, and we'll take a look and see how it does. Okay, so I got some really cool results here. I actually let it go for 10,000 iterations maximum, but it finished after like just over 1,000. So let me show you what the iterations look like. So here's what we started with. And as I keep going, you can see it's resolving all these crossings. And it's hashtag oddly satisfying, right? Look how nice this looks. I did this years ago when I first made this assignment for my class, and I remember having a similar feeling then of how good this looks. So yeah, this trick of like picking up where you left off is something that I thought of back then, and just remembered now as I was looking at those iterations. Yeah, so by the time we get to 1073 iterations, we've gotten rid of we've done all the improvement that we can, which includes crossings. So by the time we get to the end, there's no crossings anymore. So there we have it. It's traveling salesperson art. Now to do those 1,000 iterations, it only took a minute and 37 seconds, but that was actually saving these plots every time. That's really going to slow it down. If I comment out all the output that's happening there, and let me just let's restart, clear everything, and run. It'll take a second to get back to here exactly. It's just running through everything we did, doing the stipple, all that stuff, minimum spanning tree, stuff for search, etc., etc. Now, oh, this is cool. Look, This only took 3 seconds to get, let's see, it should be a little bit different each time. But yeah, if I plot this, there it is, and it doesn't have any crossings. So let me say, I'll do this a couple times, and I'll save the results, and we'll see how different they are each time. Okay, so as I was doing this, I remembered that the only source of randomness in this code is actually when we're doing the stipple pattern. Everything else is totally deterministic. So I have a seed here that I can use, so that is repeatable each time, the stipple pattern that I get. So I tried a few different seeds, and I got these different patterns here. So here's seed 0, 1, 2, 3, 4. And so what you see every time is we get a pattern that doesn't have any crossings. And so now we'll just pick our favorite one. I like seed 1 here and seed 3. Those are my favorite. I think I'm going to go with 1 for the rest of my examples here. So yeah, let me choose the seed of 1, and I'll run this again. And then I'm going to show you, okay, so this is it. This is the Traveling Salesperson Art. I'll provide this code. You can try it on any example that you want. But I want to show you some cool things that we can do now that we have a really interesting, intricate loop. So that's what this is, right? This is a cycle. This goes around. It's something that you can draw without picking up your pen, and it doesn't cross itself. So if I save an extremely high resolution version of this image here, let me show you something kind of trippy about this. So, okay, this is seed 1. I'm going to open this up in GIMP, or some image program where I can do a flood fill. And let me take this and do a flood fill. And look at that. So it turns out this is what's known, because it doesn't have any crossings anymore, this is what's known as a simple closed curve. And so there's something called the Jordan curve theorem that says that such a curve that doesn't have any crossings and actually forms a loop has an inside and an outside. And that's not at all obvious when you just look at it, right? Does that look like it has an inside and outside? But it does. And so in computational geometry, there's a lot of different algorithms that deal with simple polygons. So it's called actually simple polygon, even though it doesn't look very simple, because it doesn't have any crossings, and it doesn't have any holes either in it. It doesn't have any holes. It just has an inside and an outside. So what it means is you can actually continuously deform this into a circle, or sorry, a disk that has an inside and outside. If I were to stretch this, like if this were made out of rubber band, I could stretch that out into the boundary of a disk, and all this on the would be the inside of the disk. And this would be like a great example to test algorithms on that you're developing. Like, let's say that you were developing an algorithm to triangulate polygons in 2 dimensions. So there's one algorithm you can do called ear cutting, where you just find something called an ear, which is a triangle that you can actually, it just has, you can cut it off without creating a problem. So that's an ear, and then you just keep cutting off ears. Like your Vincent van Gogh. And then, yeah, so if you're going to test that algorithm, this would be a great polygon to test on, because it's really complicated. Even though it's called a simple polygon, it's quite complicated. Okay, so that's one thing. Okay, so for the next couple things I want to show, we're going to need to do something called re-parameterizing this curve by arc length. And so if I look at this loop here, it's made up of a bunch of line segments. Not every line segment has the same length. Like this one is a lot longer than most of them, and there's some that are a lot shorter. And so the first thing I'm going to try to do is see if I can resample the points along the curve so that they're more evenly distributed. So what I have to do is figure out the cumulative length, or the arc length, along this curve starting at the beginning. And so what I can do is construct a vector from this stipple pattern. So I'll say it's actually as simple as saying stipple order, just like that. Okay, so this is saying I want to take point at index 1 minus point at index 0, point at index 2 minus point at index 1, etc., etc. I do actually, though, have to, let's make this into a loop, so I'm going to repeat the first vertex at the end of it, because I want to say, yes, I'm going to say stipple order. It's supposed to repeat where it started off. So I'll concatenate stipple order with stipple order 0, 1. And let's do that with the loop instead. So this is just making sure that the very last point actually connects up back to the beginning again. So I will repeat the beginning after the last point, and then I'm going to do those differences here. Okay, so now what I can do is compute the length. So I'll say length. That would be sum of the squares, components of each vector. And I'll just say length less than 0, just in case there are 2 points really close to each other. And I'll say length equals square root of length. Okay, so what this should give me, so if I look at stipple order.shape, so this is a curve with 1987 points. This should give me 1987 length. If I len of length. Yeah, okay. So this has, just to draw a picture to show you what I mean. It's like, you know, I had this curve and went around, let's say index 0, index 1, index 2, index 3. So it'd be 0, 1, 2, 3, 4. And actually, let me exaggerate this a little bit because I don't want them all to be the same length for what I'm about to show you. Okay, so we got that, and then we have this curve. So I'm trying to get a, yeah, that's fine. We'll do a green curve. That's fine. So yeah, so we have this going around, and if it was just going 0, 1, 2, 3, 4, if it just had those 5 points, that would not be a loop. We would only have 4 edges for the 5 points, but we're going to repeat that first point again at the end to connect it up. That's what I'm saying here. Okay, great. So now we have these lengths, and I'll plot them. You see they're not all the same. Some of them really jump out. That's probably like the one towards the middle here. So what we could do is figure out the arc length. That is the cumulative length as we go along this. And actually I should, so I'm going to do something a lot like what I was doing up here when I was resampling the stipple points according to their probability. So remember we did this kind of thing, and then we did search sorted. I'm going to do the same kind of thing. So actually I need to make an array that has one extra element that's 0 padded by 1 on the left. So let's actually say arc length is equal to mp.zeros len length plus 1, and then I'll say arc length 1 is, that's going to be the cumulative sum. Okay, so now what we should see is something that is monotonically increasing. This is the distance traveled along the curve from point to point to point. And again, you see sometimes it jumps. It's like, oh wow, I just traveled a long distance there. I want to resample this so that it goes at a constant slope, so that I'm going at a constant speed throughout this thing. So what I'll do is I'll figure out, so let me just choose how many points I want. I'll say n new points. Let's say I'll take 500 just to start, just as an example. So what I have to do then is say, okay, I want to choose points. I'll say np dot linspace. I'll say maybe 0 up to, okay, so the total length of this curve around the whole loop, that would be arc length -1. And I'll say n new points plus 1, because actually by the time I go around the loop, I will be back at the beginning, so I don't actually want to sample that point twice. This is a trick that you do if you want to, I'll show it maybe on a more concrete example. If I were to take points evenly spaced between 0 and 1, you know, it actually start at 0 and end at 1. But let's say that I was going to loop around and 1 was actually connected to 0 again. Then what I should do is sample 101 points, but chop off the last one. And now I get, you know, 0.99. I don't sample that 1 at the end point. So that's what I'm going to do here. I've got that. These are the cumulative lengths at which I want to resample my curve. And so now I'm going to do something like I did before with the search sorted to figure out exactly where I should be placing these points. So just to remind us how this works, yeah, I'll take this, copy and paste it down here. Okay, so what we have now is the original arc length, and then what we want to do is sample this t here, and say, okay, this tells me the cumulative sum with the original points I took, but I want to sample a different speed along the curve, this equally spaced speed here, and this is going to tell me some indices that I can sample the curve on. So, all right, if I look at them, first I'll make sure the code runs. Yeah, okay. So, yeah, you can see I'm actually jumping a little bit from one place to the next. In fact, I don't really like that it's only sampled them in integers, so I need to think for a second. Search sorted is probably not going to totally cut it. Oh no, I guess what I can do is, okay, so what I need to do is, it's like, I know the first point is going to be at 0, that's fine. But the second point probably is going to be a little bit past 7. Yeah, so let me think about this for a second. Okay, so I decided actually I'm not going to use search sort after all. I'm going to use something called np.interp. So there's this method called interp in the numpy library. And what it does is it takes the first parameter is actually where I want to sample. So that would be like the arc length that I wanted to sample. That would be what I was calling t here. The second parameter is the original x coordinates, the original t's. This only works for one-dimensional functions, but that's fine. I'll just do it in a loop. There's only two coordinates. It's fine. So let me call this x resampled equals np.zeros, like, or maybe I'll call this stipple resampled. That's going to be np.zeros like stipple order. And now I'll just say for dimension in range. There should be 2, but just in case we're going to do this in higher dimensions or something. Loop through the 2 dimensions and then say, okay, stipple resampled the dth column. I'm going to make np.interp t arc length and what the original stipple pattern was. Okay, let's see if this worked. So I am going to make a similar plot to what I did here, except I'm going to plot stipple resampled. And hopefully what we'll see is a bunch of points that are more evenly spaced here. It says they're not the same length. Hang on. So my arc lengths, so let's see. Length of arc lengths is, I meant to say len of arc length. Okay, that's 1988. Stipple order is 1987. Let's see. Arc lengths. Oh, yeah. It's because. Okay, yeah. Right. I actually do need to repeat that point one more time. So I should be right. Okay. I shouldn't have been using stipple order. You probably saw it before I did. I should be using loop. Okay, there we go. Okay, let's try that instead. Oh, right. I don't want to do np.zeros like stipple order. I've chosen a new number of points here. I should just say, okay, I only have 500 points here. I'm just going to do that. Okay, there we go. Actually, it didn't close itself up at the end because I didn't actually plot it all the way there. But okay, yeah. So that's okay. It's not awesome though. I probably should take a little more than 500 points. Let's try to take 2,000 because that's actually a lot closer. Okay, yeah. So that's actually a lot more like how many points I took before. But now you can see they're much more evenly sampled along here. So let me take a second. I'm going to encapsulate this in a method, and then I'm going to use this for a couple of fun applications here. Okay, I actually set up the method so that where we want to sample the curve is going to be specified on the unit interval. So this is going to be, the unit interval is going to parameterize the whole curve. This is a pretty standard thing that you do in differential geometry when you're talking about curves. Say that 0 is the beginning of the curve and 1 is the end of the curve, which actually in this case will loop back around. So then I don't have to worry about what the length of the curve is. If I say 0.5, I know I'm halfway through the curve. If I say 0, I know I'm at the beginning, etc., etc. So yeah, I did that, did the method like this. Actually, now I can do, because of the way this is set up, I can actually do something really weird where I say, actually, I'm going to parameterize this with the quadratic function. I'm going to spend, like, I'm going to be slower at the beginning and then slowly speed up towards the end. So I don't know if you can see this, but we have a lot more points at the beginning. And well, it's hard to see. This thing loops all over the place. But anyway, just to say, I don't have to choose the points equally sampled, but I will for now. Okay. So that's resampling by arc length. So now I'm going to do something called curvature shrinking flow. So it turns out if you have a curve that's parameterized by arc length and you smooth it uniformly over the whole curve, then what will happen is the curvature, like the places where it's really like sharply transitioning, will slowly die away. And actually, maybe I won't spoil the surprise. Let me just do it. So what I'm going to do actually is smooth this curve repeatedly by a Gaussian and then keep resampling it and smoothing it again. Okay, so I pulled up some documentation of a method that I'm going to use to help me. Just in the interest of time, I'm not going to implement this manually. I'm going to use something else called Gaussian filter 1D. So this is in scipy again. So let me go up and import this. So I'll say from scipy.ng image import. So scipy is really coming to bat for us here. Gaussian filter 1D. Gaussian, I'm sorry, I like to say Gaussian. It was Gauss though. Okay, anyway, yeah, don't let me catch you saying Gauss or something like that. Okay, anyway, so if I look at the documentation, this takes the input and sigma. This is the amount by which I'm going to smooth. I'll probably play with this a little bit, but this is going to be in terms of samples, not in terms of the length along the curve. So when I say 2, that's like 2 indices on either side of the Gaussian is like 67% of the extent of the Gaussian or whatever. So it's the bell curve, whatever. I'm going to slide the bell curve along and smooth by the bell curve. So yeah, let's say, and actually here I don't have to have a loop, I can actually specify the axis along which I want to do it. So let me say stipple smooth equals Gaussian filter 1D stipple. I'll have the same variable here. I'll say stipple smoothed. I'll just make a copy of stipple resampled. And then I'll say, yeah, stipple smooth. Okay, so let's say, I don't know, I can play around with this, but maybe I should say, let's make sigma be 2 to begin with. And I want to, yeah, actually, I want to actually smooth down the columns here. Okay, let's just see what happens if I do that. And I will plot this here. Have a look. Okay, so you can see actually this is really smoothed out a lot. Now, one thing I should do though is, okay, yeah, so the mode here, I want to treat this like a loop. So when we go beyond the boundaries, like when we get to the end of it, as we're walking through the curve, we want to loop back at the beginning. So I should actually say mode is equal to wrap. Yes, wrap. That will actually take me around in a loop. Just to be a little bit careful here. Because we're really trying to treat this like a loop. Okay, good. Yeah, so now you can see, okay, yeah, you see it close the loop much better there. Very good. All right, so we have that. Now let me do this in a loop. So I'll start off, yeah, I'll start off just like this. But now I'm going to do this whole thing in a loop. So maybe what I ought to do, I'm going to keep alternating these variables here. So I'll start off saying stipple smooth equals, what's it called here? Yeah, actually, I guess I'll start off with stipple order. I'll just say stipple order dot copy. Okay, so now say for iteration in range, I'll do like 100 iterations to start with. I'm going to resample this stipple smoothed, and then I'm going to smooth it. And in the next iteration, I will resample and smooth again, and I'll resample and smooth again, and resample and smooth again. So let's make a little figure here. And let me save this in an animation. And I might as well throw in a title here too. I'll say smoothing iteration. Yeah, we'll do that. And then maybe I'll just remind us what sigma is. Sigma equals sigma. By the way, you can do a cool thing here. I could actually make this, I could use LaTeX here and make that the actual sigma. Okay, we're going to do that, and then we're going to save this to, we're going to say smooth blah.png. And actually, let me be specific here. This is called curvature, shrinking, smoothing, iteration. Okay, let's see. Did I just do anything? All right, if I go and look, I just made a whole bunch of frames here. Let me find the first one, and we can have a look and see if this is doing anything. Is this doing anything? Okay, so this is how we start off. And now look what's happening as we go along. You see how it's getting rid of that curvature? And so the other thing you notice as this is happening, okay, I should go more iterations. I need to go more than 100. I should probably go like 1,000 actually. But as this curve is evolving here, you notice, first of all, it never intersects itself. So that's one thing that's really cool. It doesn't, like, you know, it didn't intersect itself in the beginning because, well, that's all the work we went through to get rid of those crossings. But it actually will never intersect itself if I do this technique here. It'll remain as a simple closed loop. And as I keep going, what will happen actually is, so it's a pretty complicated loop, so it takes a little while for this to happen. But eventually, it will. Let's see, how far am I here? Okay, I'm about 500 iterations in. Let me just go through and see. I'm going to jump forward a little bit. Oh yeah, this is taking a long time. But eventually, it's going to turn into a loop. Or it's already a loop, sorry. Eventually, it's going to turn into a geometric circle. Looks like I might have screwed something up around the boundaries here. But this video is getting really long, so I'm going to say this is close enough. Yeah, so it's supposed to turn into like a circle. I'll see if I can spot anything I did wrong, but I'll take a look. Yeah, but it's supposed to turn into a circle and then shrink down to a dot. That's what's supposed to happen at the end of this. But already, I think it's pretty cool. Like, at the beginning, you can see that it starts off very complicated, and then those features suddenly disappear, and then eventually this thing moves out. So I'm just going to take a look at my code real quick, see if I did anything silly, and but we're not going to dwell on this for too long because I have other things to show you. Alright, so I did change the way that I was computing arc length a little bit. Now I am actually using the same method to help me compute a smoothed estimate of arc length. So that's another thing I can do. And then I integrate velocity, whatever. I'm not going to worry about that. I'm not going to explain that right now. But it didn't totally fix it, but it looks okay. So let's have a look at this video here. I'll start at the beginning again. So anyway, yeah, you could just see the whole point is it's shrinking. Also, I was more careful to keep the axes the same size, so you can really see that it's shrinking. But again, it doesn't cross itself the whole time. And eventually it's going to shrink down to a loop and then to a point. Okay, so anyway, I just thought that looked pretty cool. Let me show you something else. So this is a paper that I wrote that actually got rejected, but it's still fun. And so now I'm going to show it in this video. So because this is a loop, what we can do is use it to create a pitch. So if we think of an audio waveform, I've got plenty of videos on my channel about audio, you can watch them, but you know, I'll just show you a basic example here. So if I say, okay, we have something called the audio sample rate, and then we'll have a frequency. I'll say this is 440 cycles per second. And now I'm going to make some times. I'll say maybe I'll have 2 seconds of audio. So 44,100 samples per second times 2 seconds. That's the number of samples I need. Put this in units of seconds. And then simple harmonic motion, the equation for a sine that repeats itself, or a sinusoid that repeats itself, is 2. The phase is 2 pi times the frequency times time. And did I forget to import? Yeah, I need to import, in case you want to do this at home. I meant to say import. There we go. Yeah, so what I can do is I'll just play this. Actually, I plot maybe the first maybe 400 samples. Okay, so it looks like this, but actually it does this many times. It does this 440 times every second. So when I plot this, it's oscillating so quickly you can't even see it. Let's say audio y rate equals SR. I've done this a million times. Okay, so let's hear what this sounds like. So that's a pure tone. Okay, but anything that repeats itself is going to sound like a pitch. And if I make the rate at which it repeats itself go up, the pitch goes up. If I make the rate at which it repeats itself go down, the pitch goes down. So those are the basic rules. Okay, so what I'm going to do is, instead of repeating in a cosine over time, I'm going to take the x coordinate of this curve and have go around that, because this goes around in a loop. So if I go around it and around it and around it, the x coordinate will repeat itself. I just have to go around it the right number of times. And actually, because audio can be multi-channel, so for example, 2-channel stereo audio, you can have one audio stream for the left ear, one audio stream for the right ear. What that means is I can actually put the x coordinate in one channel and the y coordinate in another channel. And so I can actually have my audio draw this curve. Okay, so let me see if I can make that happen. So what I'm going to try to, let me try to keep the same frequency. I'm going to be mindful that 0 is the beginning of a loop, and then 1 is the end, looping back again on itself. So I want this to go 0, 1, and then jump back to 0, 1, 0, 1, over and over again. And I want that to happen 220 times every second. So what I can do is, let's say, okay, I'll choose how many seconds I want. I'm going to say 2 seconds. And then I'll say, okay, let's make this, so I'll say, okay, I go from 0 up to the number of seconds in increments of the sample rate times number of seconds. But actually, okay, so I go through 220 cycles every second. So I want to go multiply this by the frequency. And then I want to take the modulus by 1. Okay. Let me just plot this for a second so we can see maybe the first, like, again, 500 samples or so. Okay, so this is supposed to go through 220 samples a second. Actually, let's come up with an even. Let's say it was going to go through 441 cycles per second. At this sample rate, that means that every 100 samples I should go through a period. So let's see. Okay, good. Yeah, so every 100 samples I go from 0 to 1 and then back again, 0 to 1, back again. So let me use this t as the parameter that I use to resample this. So let's say here, actually, oh, I should have gone back. I want to go back to the original resampling method I had. I got a little too fancy here. Let's go back to the original. Okay, so just because I don't want to smooth this by accident. All right, yeah. So let's do that, and we're going to resample this. I no longer have the signal parameter. And this is not going to be stipple smooth anymore. This should be, we're resampling stipple order. Okay. That did something. Let me actually plot the first coordinate and see if it goes through. Yeah, maybe I'll just go again through the first 500 samples. Okay, anyway, this looks like it's repeating itself. I don't know what it didn't like here, what it did wrong. Oh, I tried to put a plot into a plot. Okay. Yeah, so anyway, that's the first, yeah, so look, you can see it's repeating itself every 100. If I plot the second coordinate, it's also repeating itself every 100, but it has a different shape because that's the y coordinate. It's doing something different from the x coordinate. Okay. What happens if we plot these? Let's do a scatter plot. And actually, let me call this y, okay? Because this is going to be the audio. I call that y. For y? I don't know. It's usually output of some function y. Okay. So let's plot these two coordinates next to each other. And what we see. Okay, let me get rid of this now. So we plot these two coordinates next to each other, and actually I probably should have done it the other way around. Oh yeah, it's upside down again, you know, it's that thing, whatever. Okay, anyway, that's my penguin. But actually this is an audio waveform. So it's looping over itself over and over again. And yeah, I can listen to it. Let's hear it. In fact, I think I have to send along the transpose here. Okay, let's listen. Ooh, okay, it's very buzzy. Hopefully, I'll check make sure I'm not blowing you out the audio out here. So compared to the pure tone, it sounds a lot buzzier because it has a higher frequency content in it. It's not just a simple tone; it has a lot of harmonics. And I can change the pitch. Let's see if I change this, make it a lower pitch. What does it look like? Okay, it looks kind of similar, but it sounds pretty different. I actually made a little website that hang on, let me bring up this website. Okay, so this is a website I made. I submitted this to ISMIR back in 2022. I was very hopeful that it would get into ISMIR, so I did an example with traveling salesperson 2s on the ISMIR logo. This is okay, maybe a humble brag. This is the only ISMIR paper I ever submitted that got rejected. That was okay. It was really fun. And now I get to show you. So what I did here, I actually showed that you don't just have to go through at a constant velocity. You can actually change the speed at which you go through the curve. And you could do something that's like something called FM synthesis, which I talk about in some other videos. But so here's an example with the ISMIR logo. So again, on the x-coordinate, I'm plotting what's in the left ear, and in the y-coordinate, I'm plotting what's in the right ear. And yeah, it's actually, you could give it a different timbre. Like you can change the sound by going through it at different rates with this FM thing. So that was like, we called that dirty bass. Okay, that was something I found when I was teaching my music class. Oh yeah, I threw in there some amplitude modulation too. Like I would turn this down too, and I did that with the curvature shrinking flow actually. So actually, you know, it gets quieter because when you shrink the curve down, it gets quieter. Just to show you can also make like a trumpet sound. And you can draw Usher's face if you want. What else we got here? Oh yeah, electronic bell. Alright, so we got that. A student in my class I was teaching at the time really liked this song. So that, yeah, anyway, I'll link to this in the in the description if you want to check it out. Actually, I probably should find that code and publish it. It's on GitHub somewhere. And maybe I'll post the paper. Why not? It's whatever. It doesn't matter. So cool. Anyway, I hope you enjoyed Traveling Salesperson Tunes. There is one more thing I want to show you though. There's just so much we can do with loops, and I'm only just scratching the surface here. But so what did we do so far? I showed you the inside-outside thing. I've shown you how to do curvature, shrink, and flow. Now I've shown you how to play tunes with this because it repeats itself, so we hear that as a pitch. If we go back to some more fundamental ideas, any loop can be described in something called a Fourier basis. Okay, so in order to do this, I actually have to convert my stipple pattern into a sequence of complex numbers. And so I'm going to take this variable called stipple order, which holds my pattern. I'm going to say, okay, let's say y is equal to stipple order 0 plus 1j times stipple order 1. Okay, so what this is saying, what on earth is this 1j? This is a number whose square is -1, otherwise known as I in complex numbers. So if I say 1j times 1j, I get -1 plus 0. Okay, so this we're in complex numbers now. We're going to put the first coordinate of the stipple pattern in the real part component of each number, and the second coordinate in the imaginary component. So if I look at this now, this is now a sequence of complex numbers, real plus imaginary, real plus imaginary, real plus imaginary. But really it's like a sequence of just one number now instead of a sequence of two coordinates. It's just that the way complex numbers work, we can kind of get two coordinates for the price of one. But anyway, actually, this is going to allow us to use this Fourier transform, which also works over complex numbers. So let me just do this, and bear with me, and we'll just see what happens. I won't go into all the math, but I'll just sort of show you some of the ideas. So if I were to say here, Fourier equals np.fft.fft, this is now going to compute something called the discrete Fourier transform. This gives me another sequence of complex numbers, which has the same length as the input. Okay, so those both have 1987 elements. But if I were to scatter, so I'll say the real component, or I guess I put the imaginary component of y first, and then the real component. So, okay, so just to show you, this is the original stipple pattern. But if I were to plot the Fourier that way, I would see that actually a lot of the numbers are much less significant than others. In fact, it'll be a little bit easier to see if I plot something here called the magnitude. So if I say magnitude is equal to np, the absolute value of Fourier, Okay, so what I can see here is that most of so the magnitude is it's like the length of the vector. If you think of the complex numbers vector, it's the square root of the real squared plus the imaginary squared, and so we can see that most of those numbers are very small. So what I can do here is say, okay, let me figure out what is in the 95th percentile of magnitudes of these Fourier coefficients here. And so that is 4005. If I plot this again, that looks about right. So this is going up to a million here, so 1.4 million. So yeah, apparently 4000 is about 95th percentile. Okay, I can believe that. So what I'll do here is, let me say, okay, let me shrink down. I'll say Fourier, every place where the magnitude is less than that amount, let me make that 0. And now I can do something called the inverse Fourier transform. So I'll say this is fft.ifft, this is the inverse Fourier transform. And okay, so let me go ahead and plot that. So I'll say y, imaginary yn, real. Let's see what that looks like. Okay, so this is like kind of an approximation of my penguins. If I were to take somehow like the 95, or the 5% most important Fourier coefficients is what these are called, then I would create this pattern. And what's cool about that is like it's a lot, it really captures a lot of global information. If I was just to take the top 5% of the original coordinate magnitudes, I wouldn't see such a nice pattern. Actually, let me try that. I'll show you. So if I were instead to say, let's make this the magnitude of y, and I'll just say y is this q is equal to 0. Let's just see what that looks like. So if I were to plot y, yeah, if I were just to take the top magnitude y, I get just complete crap. I just get like, okay, so coordinates that are furthest away from the origin. So this is somehow not a good basis for compression. On the other hand, if I use these Fourier coefficients, I have a very good basis for compression. It's like, okay, I'm preserving in this case, mostly the low frequency details a lot more, like the overall shape, these global patterns. Let's keep maybe just the top 90%. Okay, so you see I have a little more detail there. If I keep the top 50%, I can make out the penguins a lot better. So that's actually not bad. It's like drop 50% of the information, although you do need to remember what positions they're in. So you have a little more information. But basically drop 50% of the information, you still can kind of preserve the pattern. Let's say drop 75% of the information. Not bad. Let's try to drop 99% of the information. Okay, so unlike curvature shrinking flow, there's no guarantee that this thing is not going to cross itself, but it is another way to kind of like slowly remove detail from this thing until you don't notice it anymore. Now I have to decide. We've done a lot, and this is a long video. I could try to take a minute and do an animation showing how this is actually just like summing up a bunch of circles. But I think I might have to table that for another time because this has been a really long video. So yeah, let me provide this video for you, and I'll link the source code. And let me know if you do anything with it. And then maybe someday I'll make a video where I talk a little bit more about Fourier and how you can interpret it as circles. In fact, I actually do have some other videos on this. I'll link to those. I thought I was going to make an animation like drawing penguins with circles, but I don't know. The compression's good enough. Let's just leave it at that. Okay. So I hope you enjoyed. Thank you so much for watching and getting this far. And I'll see you next time. Oh man, I almost forgot to show you the coolest thing. So I ran this an assignment related to this 3 times. And I had an art contest where my students did all sorts of cool stuff with this. Some of them just, like the stipple patterns. Some of them went all the way. They were using different color maps. Yeah, some of these stipple patterns are pretty good. Check that out. Some people actually just like the Delaunay Triangulation or the minimum spanning tree. This can look quite cool too. This is a good little one. Try to make that, put that to a tune. Let's look at the next year I did this. What we have here. So I'll link these. Definitely some cool stuff. We'll check out Mario there. Charlie Brown. Marshmallow, look at that. There's the Doctor Who. And then, oh, Peter Griffin. Not sure who that is. Probably people watching this know. Did I just out myself as not enough of a nerd? I don't know. Check that out. That looks pretty cool. Nice color map there. Some people had a little trouble getting the crossings, but they still made some progress. That looks like my face with a lot of crossings. And yeah, so lots of cool examples here. Check that out. So yeah. Oh, there's my head again. Students always like to put my head onto things. This one always cracked me up. Get stick bugged lol. So that's actually kind of a cool thing. You can trace out letters this way. So it's like a weird form of cursive. You never have to pick up your pen. Ooh, minions. Look at that. That is Pat. One of the 3 Pats that I had in. They graduated the class, the last class I ever taught. Before I stopped being a professor. Okay, now it's all good. Alrighty, so hope you enjoyed that. I would love to see if you do your own little art contest submissions. Please share. Take care.